Okay, sorry guys. I just started taping now. We're on vertical and horizontal asymptotes. Maybe when seventh hour leaves, I'll go backwards and show our ideas here for those that might have missed. Okay, but anyway, on this one, I was going to go ahead and do the fraction button that I do have, 1, and then it just does this. And I think it was 5 over. I just arrow down, and I don't have to do parentheses with this one, so that's a nice thing. So if you have this option, go ahead. If you don't, then do the denominator in parentheses before you hit the slash bar thing. I think I'm in Zoom Standard. Whoa, this is weird. But watch the y equals 0 thing. Whoa. So is that a horizontal asymptote? Yes, it is. It's because the numerator's degree is 0 and x to the 0 equals 1. So that's why the degree of the numerator is 0. And the degree of the denominator is 2. Or think of it this way. I plug in a million, you get 5 over a million squared. That's 5 over 1 followed by 12 zeros. That's infinitely small. It's y equals 0. Now what happened after that? There was no vertical asymptote because this leads to an I number when you try to find the zeros of the denominator. I numbers don't graph on a real coordinate plane. So that's why that graph doesn't exhibit any vertical asymptotes. So one way or the other, analyze the behavior and say, okay, it does look like there's a y equals 0 asymptote. Or take it a step further for chapter 2. Okay, so for those in the video, I did a whole asymptote thing, and I think that's all I've done. So at the end of the notes, I'll synthesize that after 7th hour is done. Okay, don't write all of this, but write our next thing. Okay, so on our cheat sheet, that 9 sections, local and absolute extrema would be one of the sections. So this is a new concept. You know, put a star here. Now to something different. I put under the word local, put relative, and I'm moving this up here so I don't have you write from the box. Don't write the boxes. I'm actually going to have a picture, and then we'll define the terms by the picture, and it'll make complete and total sense. But I do have to do some calculator training with you. Do not write the blue box. But there are going to be local maximums and local minimums. These are all called relative extrema or absolute extrema. So this is the word that is both minimum and maximum. So maybe you need to know that as a term, but I have that up here. Extrema just means that's the overall term for maximums and minimums. So you already wrote that word. Okay, and then this is where we're going to define it. And I think something happened with my part of why I'm having problems. We don't know about that. I had problems 5th and 6th hour with my notes showing up. Computer issues of some sort. And I don't really care about this point. This is called a point of inflection. If you go to calculus, you'll find out about that. Don't even write that. Okay? Just got a little wiggle in the middle, but it's not pertaining to this. Okay. We can assume that this goes forever this way and this goes forever this way. This is why I don't want a formal written definition of relative extrema and relative minimums and maximums. Relatively speaking, localized in this little area right here. Like it's just like saying, hey, what's the best restaurant in Lockport? Oh, it's the Landing. But is that the best restaurant in the world? No, locally speaking, it may be considered the best restaurant, but in the world, no. So this is a local or relative minimum. Now you're probably like, this is insulting. Of course, that's a low point, and locally this is easy. Listen, this is the minimum, so the minimum equals 2. Where the minimum is located is called the x value. Where located? See, this is a terminology that you'll see in any like situation. Where it's located is the input value. The word minimum describes the y. So it is 2. And why is it only local? Because this goes forever down. There are lower values later, you know, so only locally speaking is this a low value. All right, very simple term, I think. It's very simple logic, English-wise. That's why this is only a local max. The local max, let's put it this way, equals 7. Where is it located? 5. That's how they word this. So really what I found out is, I mean, back in the day when I was a rookie teacher, I'd ask, hey, where is the local maximum? And the students would write 5, 7. Like, yeah, that's good, and I would move on. But actually, I was wrong, that teacher. What is the minimum? It's 7. I'm sorry, maximum. Where is it located? 5. Okay, so we'll see how it goes. I think we'll say list it as a complete coordinate, then it allows you to just write the coordinate. And then just do one more graph like this because, even though I'm going to have one that almost looks exactly like this later. Okay, there's a local max, there's a local min. I'm only going to write this one for our definition purposes. That is an absolute minimum. There is no lower part of this graph that exists. Don't even write this one. So that's the only time you get an absolute min or maximum, when no other part of the graph exists below that point. There is nothing more. So everyone okay? Anyone? Like Ali jumping in that one time? Yeah, then actually what Mayasar did, that's awesome too. Throw questions in the chat. I do have them open. Actually, fantastically awesome. Like I said, this will be easy to put in our little 9-chart cheat sheet. Holy cow. Did he just swear? No, I said sheet. That was sheet. This, maximums and minimums, very simple. It'd just be this picture, really. You can almost put that in one of your 9 things. Just, blah, 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 blah. Let's find the maximums and minimums. Okay, as of, oh, excuse me. As of, boy, he sneezed and he coughed. I'm fine. Everything's fine. No COVID. You don't have to write all these directions. Just find maxes and mins, blah. Find extrema, blah. Okay, so as of right now, you can use your graphing calculator. But when we get to chapter 2, we got a whole big chunk of polynomials and analyzing them and doing them without a calculator. This one will always be a calculator puncher. So I'm only going to do one on the calc, and then I should only have to show you this one time. Because you should have done this before, I hope. But even if you have, you get one chance of seeing it like it's brand new. So I'm not saying I'm not doing that, but we got to inform you of it and move on, because this is supposed to be refreshing your mind on stuff. So I'm going to go ahead and take the minute to plug this in. I don't need that y equals 0 anymore. And then x caret 4, oh, this is a stimulating video on YouTube later, minus, hey, let's watch the guy that does math and plugs things in the calculator. That sounds like fun. Plus 6x. Million views. All right. I think I'm standard. Zoom standard. And then we'll go ahead and... Oh, that's taking forever. All right. I'd like to see this. So trial and error from the other hours. I put -20 as a minimum for y, and it still cut it off. So I'm going to go to -30. Trial and error. Keep playing with the y windows, and I want to extend the y minimum because I was cut off on the bottom. There we go. Okay. If you haven't done this before, fine. Majority of you should remember this, though, so this should spur a memory. Hit second trace. Did I say you have to have a graphing calculator? Yes. You don't have a graphing calculator, it's impossible to do what we're going to do next. And the first thing that I was going to do is find the minimum, 3. So I hit second, calc, then I'll just arrow down in case that was too fast. Minimum. Now, students in the past didn't know their left from their right. But I think also technology wasn't like it is now. I think you guys being technologically able, you deal with technology better. Hey, a compliment for the whole people of today. Here's left. Like I'm saying, students like in 2009-10 didn't know their left from their right. They wouldn't get the left bound in the left side of the graph or the left part of the hump, and wouldn't get the right bound to the right of the hump. They would get them reversed. They didn't know their left from their right. I'm not kidding. And then these arrows point at each other. So that's what it's saying. The calculator is looking for the lowest y value in between this situation. Now, the older calculator you have, it doesn't look as nice, but arrows. Now, guess, it's irrelevant. Just hit enter. So left bound enter, right bound enter, guess. And do that until you see minimum. Negative 2.05, comma, negative 24.05. I know for a fact last hour I accidentally put positive 24.05. And guess who said something? Put that in the chat. Take a guess how many students made a correction for me and said, hey, Mr. Samuelis, I think you made a mistake. And you put positive instead of negative. Jessica, you are correct. Nice. All right. Give yourself a pat on the back. All right. Now, I don't have to write the rest of these, but I will show a maximum now. I'll minimize in case you wanted to see that. But it's going to be, well, you can see me doing it here, so the screen's kind of nice. Second, oh, we're on YouTube there. I just ripped on 6th hour. I don't care. I couldn't care less. Makes me sad when I'm sitting here all by my lonesome teaching the notes and I ask a question and then all I hear is, hold on. Okay, that's good. Maximum. Now, left bound. I'm actually left of the maximum I'm trying to find, but I'm going to scooch a little closer. But I'm still left of that hump there. And then I go right of that hump. It doesn't matter. I could keep going even around that other end. Well, no, you better watch it because it'll give me high values on this thing. So you better stop there. Enter, and then enter. And then I'm not writing this one down. 0.5 would be a good rounding point. 1.3. Remember, this is the minimum. This is where the minimum occurs. And then the maximum, you can put that one, and then it's redundant at this point. Okay, now just making a point, even later, we're not going to know how to graph this without a graphing calculator, at least in this class. We're just going to go ahead and chug it in there and plug it in, and then know that we have a minimum and a maximum there. And they're both, actually, this is an absolute maximum, believe it or not, because this is absolutely the highest the graph goes anywhere. This one does go up to 0 here. Very easy to figure that out. Negative 3 plus 3 is 0. Square root of 0 is 0. 0 times I don't care is 0. All right? So you do get negative 3 comma 0 there. But you also get 0 comma 0 as a point. So actually, that's an absolute maximum there when you go ahead and find it on the calculator. Time to move on to range. This one's going to be a little rough. Okay, now listen. And I know there's a lot of you. I can see you taking notes. And you non-note takers, well, you do make me sad. And I'm going to put that right in the chat. You take notes so you activate your brain more during this. But when we do range, go back up to the domain notes for 1, 2. I'm going to use the same equations. It's a big mic check.
Yep, I'm here.
You know what? I now have to cut that off of the YouTube video. I said your last name. You could sue me if it's in there. So if I forget to do that, Elizabeth, you can sue me. You got it?
That's okay. Thank you.
Okay, you're welcome. All right, so range is y. All right, find the range of each in the graphically blah, blah, blah. Okay, good note takers. Isn't that the first example for a domain? Yes or no? Can I get a thumbs up from note takers that it did what I asked? Okay, got a thumbs up from a couple. Nadia, I don't see your face anymore, but I did see that hand. Nice. That's a good fan in your room. Cool. All right. Now, I can leave that in because I didn't use your last name. All right. So, here's the domain. We did that already. Negative 3 to infinity. But this is how you analyze that on a graph. Here's x, and here are the x's. And it looks like the graph exists for all of these x's. So, and it looks like it goes forever. So I can surmise from the graph that's what the domain is. What's the range? Well, it's the y's that are covered. What happens when I plug in negative 3? I end up getting 0. And then when I plug in these other x values, the range values actually are here. These are the corresponding y coordinates. And this does rise forever, just slow. So it does have a range value of all the way to infinity. Or think of it this way. I plug in 1,000,000 for x, and you get the square root of 1,000,000 of 3, which is still a big number. I plug in 1,000,000,000, square root of 1,000,000,000 plus 3 is an even bigger number. The outputs keep rising, and that means that is what we got there. Mrs. Westberg, which we can say her name, actually pulled a chart out, or the table, and actually analyzed the table for the range as well. So that's why we get what we get. That's actually for the next one. My bad, dogs. Because that table doesn't correspond to that one. Rough. Okay, now domain. Remember the complications for domain on this one. This is reiteration of the notes from Wednesday. And I think I got this done before I had to go to a video. You can't plug in negatives. Square root of a negative is an I number. You can plug in 0, but you can't plug in 5. So that's why they graph, oh, right, y equals 5. I'm sorry, that's so bad. X equals 5, vertical asymptote. And then that's why this graph just stops here and doesn't do anything after that. We're going to talk about this behavior at the end of the notes. Union that with 5 to infinity. That was our domain because you could see this graph goes forever. So forever after that. Oh, All right, so now it's time to think about the range. I just went like 5 times annoyingly. Did you know the square root of x is the same as x to the 1/2? And if you say no, where were you for chapter PR? Okay, we did do that as one of our things, what a radical is compared to a fractional exponent. And what I want to talk to you about is the numerator's degree is actually smaller than the denominator. So yes, this behavior that you recognize here is asymptotic horizontal behavior at y equals 0. So either high level or wait a minute, I noticed something here. That's the asymptote thing that Mr. Samuelis was yapping about. So what that means is, oh wait, you plug in 0 and I do get 0. Oh, I'm a buffoon. I also made a mistake in 5th hour as well. 0, 0 does exist. So it does exist here. It just doesn't exist out here. But overall in the function, it exists. So that was a high level range question. I'm telling you right now, the hardest thing of 1, 2 is probably going to be range. There's some little tricksters in there. And I made another mistake in 6th hour. I'm going to have to come back to that probably on Monday. Because I really focused on this and I forgot about that first 0, 0 point. So 0 is a range value, all right, even though it's not out here because of the asymptote. So good one. Anyone have any questions on that? That's a rough one. Another kick in the stomach there. Range is going to be the toughest thing. Some of these other things should be super easy. Just real quick on this one. You know, you type this in the calculator. Remember I told you, go to the domain notes. Remember, x could not equal 0 and x could not equal 3. That's because there's vertical asymptotes there as well. Well, because of the naughty values, we get vertical asymptotes. But here we go again. Look at that behavior. The degrees are smaller than the degrees on the bottom. So there is a y equals 0, but here is this graph, and it does exist forever up and down. This graph alone covers every single y value. So I couldn't care less again what happens here and there. The range is negative infinity to infinity. You should already have the domain with the interruptions at 0 and 3 written from the notes. So it's telling you to go to the domain notes. You already have this written down. All you had to do is write range. But in case those that didn't take notes after my little negative statement about those that don't take notes, maybe I'll leave it there. Okay, this is a weird one. Remember the domain went from 2 to negative 2, and then I showed you this would be one that you'd have to look at your graphing calculator. Wow, that's a weird graph. Very strange, from 2 to negative 2. And I'm not going to do this completely and totally, but I am going to do the range with giving you an idea that we already did. You could see that this is not a one-to-one function, fails the horizontal line test. It is a function, vertical line test. Everything that I've showed today all pass the vertical line test, so they're all functions. But what happens for the range? Well, it looks like only these little y values are covered. Look at this when I color the graph. I wish I had time for the chats, but wouldn't you agree that that point right there would be the low y value covered, which would therefore be called the no time minimum. So what you could do is go to the calculator and find the minimum left bound, right bound. You get an x comma y, and it is the y that you want. What is that low y value? Therefore, that is the range. So you just have to do one little thing that I already showed you, how to find a minimum on a graph that you already see through left bound, right bound. And that should make total sense, I hope, if you understand graphing is inputs, x's, output, y's. Since the graph exists here, these are the y values that are covered. Instead of a highlighter, I'm doing like a smash there just to get you to understand how I analyze that like that. Okay? All right. Again, we have these pictures in the domain. We should not have to rewrite these. Again, I'm making a video though, so we can do this. Remember the domain for this? Well, look, here's 4. When I plug in 4, 4 minus 4 is 0. So I can plug in 4, but then I can't plug in 5, 6, 7, 8. Who do we appreciate? I have to plug in x's this way because of square root of negatives. So the domain is negative infinity to 4, which you already had. That's wrong. Oh, my spaghettified brain in this e-learning environment. Oh. What happens when I plug in a 4? 4 minus 4 is 0. Square root of 0 is 0. 0 plus 5. And I look up here. Here is 5. So this is I'm doing both. I'm doing like being smart about input output, or then I'm going to what if I just someone that looks at a picture and it looks like this is at 5. Oh, okay. When I plug in 4, I get 5 as an output value. And then it looks like when I plug in other values, the y values keep going up. And if this graph keeps going up, it certainly does, then these y values keep going up. So the range is 5 to infinity. This is how you do range, my silly little friends. All right, and then just going over this real quick, I think I broke down the asymptotes. That affected the domain. But what about the range? We got a weird thing going on here. Take a breath for a second. Yeah, I do have 11 minutes, so. Oh. Alrighty then. Good enough pause. This is what I mean about you look at a picture. Looks like we got that tapering off thing again. Let's look at the equation. Oh, wait. I kind of remember something Mr. Samuelis was saying, that when these powers of highest degree in numerator and denominator are equal, then you know what? Wait, let me. Oh, this looks like -1. This is how you put it all together, folks. Then it solidifies. Okay, if I put y equals -1 there, it looks like the graph is behaving towards that. Yes. Yes, 1 over -1. Yes, the connection's coming through. But how does that affect range? Holy cannolis, does it affect a lot. Remember what I told you about range? What y values are covered. By the way, not 1-to-1, but it is a function. Does pass the vertical line test. All the way across. Only crosses the graph once. But let's look at the y's. The y's that are covered 2 times, not 1-to-1, all of these forever. So it's the y-axis that I concentrate on for range. It's very simple. It really should be. It really should be. Negative infinity to. Okay, now what happens up here? The philosophy and idea of an asymptote is it cuts off the graph and it never gets to it. So -1 is not quite in the range because the graph is approaching -1. That's what a horizontal asymptote is. Now again, just hold this thought. I'm going to come right back to it. What happened on this one when there was a horizontal asymptote? It didn't matter. There was another graph that covered those y values that were restricted by the ends. So there's the difference between these two that you have to really think when you're analyzing range. But then we got another issue. There is a big gap in the range right here. The graph does not exist for these y values. As a Fatteramact, the range begins again in what's called the minimum. If anyone said that to themselves. So you go to your calculator and find the relative minimum, and whatever that y value is, that is the start of the next chunk of the range. Whatever that y value is, why is it off to infinity? Because then the graph starts taking off and covering all of these y's. So I've colored the y-axis because y-axis, y's, that's range. And only those colors are the range that exists for this particular graph. But you got to know about asymptotes, and I made another mistake. Whatever that y value is, that is part of the range. Good. I like making these little mistakes, but then catching them. Doesn't equal, yeah, doesn't equal -1. Yes, go ahead.
Wait, okay, I'm a little confused. So when it goes to negative infinity to -1, why wouldn't that be to like -2? Because the top like part of the graph, the parabola, it like ends at -2.
The top part of this graph actually ends at, did you find this minimum? It looks like it might be 1, actually. Or actually, you know,
I didn't
it's
even
3/4.
but I'm just saying like off like the looks of it.
I think actually this is 3/4. I just looked at the equation. When I plug in 0, I get 3/4. So actually, I could put that in.
Oh, okay.
All right, that's the low point of this. There is nothing in here. The graph doesn't exist in here. The next part that the graph exists for y is that up to that asymptote. So that's what we really have to focus on. Okay, but I'm glad you said something, because when you said the minimum of that, it does kind of look like a parabola. It actually is 3/4. Doesn't go down any further than that. So, okay, good questions. Love it. I think I only have one more thing. Oh, this is so easy. Okay, this one is going to be like a super fast. It'll be one of your 9 boxes. Bounded. Actually, a couple of things that we had up there were bounded. Not related to 100% with asymptotes. There's some differences. And actually, I don't think I even have I have one little example of it, because it's such a simple concept. And it will take one of our boxes, and it'll be good to have you. I really hope you do the 9-box thing and are with me on Monday. You've looked at the ed puzzle. You've finished up your Wednesday notes. So now everything I put in that box, like in 10 minutes, you're going to be like, okay, that's a good putting it all together thing in a simplistic format. This is why boundedness is so easy. A function is bounded when the range is not going to positive or negative infinity. Okay, so the range is not going to positive or negative infinity. Well, I have to give you 2 examples at once. It is not a horizontal asymptote. It's about at the top. Is there something that controls how high or how low the graph goes? And the answer to this one is no. The graph at some point goes off to positive infinity, and at some point goes off to negative infinity. So not bounded above or below. But then when you look at this one, this is a classic x to the 4th graph. Oh, that is an absolute minimum. So that is like there is some sort of boundary limiting that this graph can go any lower than that. That's the best way I can think about it. It's just said to be bounded below. Because below there is a minimum, it doesn't go any lower. It's like a boundary. What's a boundary in basketball? You go out of bounds, foul, or you lose the ball and it goes to the other people, the other team. So there's a boundary at this graph that limits how low it goes, bounded below. It's so simple, I think, to actually analyze this. So think about this. If I gave you an equation and asked if it was bounded, you'd real quick have to snap it on your graphing calculator and then just see, does it look like this? Does it have a boundary below? This one is bounded above. Okay, that's another classical x to the 4th. These are both absolute maximums if they are at the same spot. So that's a bounded above. It seems to have a boundary above that limits how high it can go. That's the way I just kind of verbalize it. Then real quick, this is why you just, real quick snake this graph. Yeah, this is why we do graphing, by the way. Graphs are all over the world. And when we analyze data, the more data we analyze, the more succinct we can predict weather and do this other stuff. The graphs are all over the place. Believe me, they control your lives. But this is like a cardiogram, like seeing like how quick your heart's beating or whatever. It goes up, down, up, down, up, down. Never goes off to infinity, top or bottom. Didn't say this. I wouldn't be mad at you if you said bounded both above and below, but the term when it's bounded both above and below is just bounded totally, just bounded. But if you said bounded both above and below, I would not mark you wrong. And I think a math teacher that would is kind of mean, because you're not wrong when you say bounded both above and below. Now, the one example I wanted with this was just to remind you of exponential functions one more time. Exponential functions do have asymptotes. All right, and I did have an example of this. So not to go over this because I only have about 4 minutes with you, but this does have a horizontal asymptote at y equals 0. It's because when I plug in, that's a y. When I plug in 1, 2, 3, 2 to the negative first is a half, 2 to the negative second is a fourth, and I'm getting the negative because it's built into the exponent. 1/8. As I keep plugging in big numbers for x, these y's approach 0. So this is bounded below. So an asymptote can be a boundary if it is the graph doesn't go anywhere on the other side of it. Doesn't have to be an asymptote, but it could be. It's just bounded below because there is a boundary. All right, I'm going to end with end behavior. Nice, I like that. End with end behavior. I'm going to go with it real fast. And I think this one's a review. This would be one box in your cheat sheet. So this is another concept of analyzing functions. Hey, what's the end behavior? And actually, we have something else with asymptotic. Let's focus on this one real quick. Real quick, snap an upside down parabola. And then this is what the notation is. I hope the dog that you have seen this before. Again, all of this is supposed to be review, but I am teaching it as brand new. But hopefully your teacher did say this. What does LIM f of x mean? Well, it means what does y approach? That's just a fancy mathematical term. What's the limit of y? But really what it means, LIM is limit. What does y approach as x approaches, and then any number could be in there. But for end behavior, infinity and negative infinity. So this is why this should be easy, folks. Input, output. When I plug in x's and get bigger and bigger and bigger, input, output, input, output, input, output. But then as I plug in these x's, my outputs end up coming way down here. When I plug in this, I'm getting off the screen, man. So what is the limit of y as x? What does y become as x becomes infinity? Y becomes negative infinity because it's going forever down as x goes forever to the right. And then the same thing with x's to the left. When I plug these in order, this goes down forever. All right? So the limit of f of x as x approaches negative infinity is also negative infinity. Now, feel free to stick around. I'm done. But I'm going to continue with the video and do this one. If you want to stick around and see it now so you don't have to watch the end of this video, go for it. It's not going to take me long because we are going to do these limits when we approach a vertical asymptote. So I think you should stay, but if you're leaving, then you should watch the end of this video when I post it, but we'll see. And then also on this, so you can see, look at this, y equals 3. That's a horizontal asymptote. So a couple limits on this one. First, just like the last one, the limit of f of x as x approaches infinity. As I plug in big numbers for x, I am getting numbers that keep getting closer and closer but never reaching 3. So that is a much different answer when you have a horizontal asymptote when you're plugging infinity and negative infinity. Almost done. And feel free to stick around if I go through anything too fast because I'll be here for you. I was going to meet someone at 11:45. I hope I said 11:45. I think I said 12:45. I got my numbers all screwed up. When I plug in a negative number, I'm still approaching from the other side this horizontal asymptote. So when I plug in x as x approaches negative infinity, you actually approach 3. Now this is really why you should have stayed. Because now what we're going to do is these are not end behavior per se, but in a way they are. We're going to analyze what's going on with this and what's going on with this. And what's going on with this is that vertical asymptote. So what does y approach as x approaches this vertical asymptote number? The vertical asymptote's at -2 from the right. That's what that plus means. From the right. It's a very tougher question for the students, but if you just look at what I do, it's like, what happens when I plug in these x values from here to there? Input, output, input, output, input, output. Uh-oh, it's starting to turn. And then as I get infinitely closer to x, this is what happens to the y's before I hit this vertical boundary of plugging in -2. So the answer is it goes off to negative infinity, the y's do, as I get closer and closer to -2 from the right. I hope I said right there. And then what's the limit of f of x, last one, as x approaches that vertical asymptote from the left? Negatives are on the left side of the number line. Positives are on the right side of the number line. So that's why that's the notation. So as I plug in these x's and I get closer and closer to this boundary, this is what happens to the y's. Booyah. Goes up to positive infinity. Thanks for staying. Shows that you care. Just to finish it off in just an extra 2 minutes. That's all I asked. Those that left, whatever. Can lead a horse to water. What can't you do? What can't you do? Can lead a horse to water, but you can't. Come on, put it in the chat. Come on, make my day for the weekend. Someone put, you can lead it. Thank you, Nadia. I appreciate it. Have a good day, everybody. We'll see you. Any questions, fire away.